So welcome to our video today. We're going to be talking about topic 7.11 of the AP Chemistry curriculum, Introduction to Solubility Equilibria. So obviously, given the name of solubility, we're going to be talking about solubility. So solubility just means, has to do with when a salt is placed in water. So let's just think of a salt you're very familiar with, NaCl. We tend to say sodium chloride is a soluble salt. And so what that means is if you take solid sodium chloride and you place it into water, we tend to think it is going to break apart into sodium ions, which are aqueous, and chloride ions, which are also aqueous. And so this is the way we would write the solubility of sodium chloride. And being a soluble salt, we write a one direction arrow saying that it breaks apart completely. Some salts, though, are very, very insoluble. And so we also want to talk about those salts. What happens to them when we put them in water? For instance, if we have barium fluoride, if you looked on your solubility chart, you would see that it is insoluble. But to a very small extent, some of the barium fluoride will break apart. It forms an equilibrium where some of the barium fluoride will break apart into barium ions, aqueous, and fluoride ions. And since there are two fluoride ions, we write it down as 2 here because those two break apart from one another. So 2 fluoride ions, which will also be aqueous. So this is the solubility of barium fluoride. It only happens to a very, very small extent, though. It forms an equilibrium, meaning that we can write an equilibrium constant for this expression. K, the equilibrium constant, is equal to our products, which is barium in its aqueous form, times the concentration of fluoride in its aqueous form. Since there's a 2 coefficient, we need a 2 exponent here. And then in the denominator for the reactants, we're not going to put anything because barium fluoride is solid. It has a constant concentration. So we don't put solids into the equilibrium expression. So this is the equilibrium expression for the dissolving of barium fluoride. When we talk about dissolving, we give K a special name. It's called Ksp, which the Sp stands for solubility product, because it's the product of the 2 ions that have dissolved into the solution. So Ksp is the solubility product, and it's simply the product of the 2 ions that have broken apart into the solution, each raised to their coefficient power. So it turns out for barium fluoride, if you look up its Ksp value, its Ksp value is 1.84 times 10 to the negative 7. Notice this is a very, very tiny number. That means that very little of the barium fluoride will actually form barium ions and fluoride ions. So if the barium fluoride starts dissolving, it will only dissolve until there is the product of these 2 ions equals 1.84 times 10 to the negative 7. We tend to think that if the Ksp value is less than 1, then the salt is insoluble. And so the lower than 1 it is, the more insoluble it is. For Ksps greater than 1, we tend to think of those as soluble. So for NaCl, the Ksp is very, very, very large because NaCl dissolves very well. But BAF, barium fluoride, dissolves very little, and so it has a very tiny Ksp value. So one of the things we can do with Ksp is figure out what what's called the molar solubility is of a salt. How many moles of barium fluoride will dissolve per liter to make barium ions and fluoride ions? Now, if you'll notice in the stoichiometry here, for every 1 mole of barium fluoride that dissolves, 1 mole of barium ions will be produced, will dissolve into the solution. So if we can figure out how many barium ions are in a solution per liter, then we know how many barium fluoride formula units dissolved in that solution. So we are going to calculate what's called the molar solubility of barium fluoride, of BAF2. So to do this, we're going to use a Rice table. So barium fluoride, solid, produces barium ions, and those are aqueous, and fluoride ions, 2 fluoride ions, and those are aqueous. And initially, right when you put some barium fluoride into water, you are going to have 0 molar barium ions and 0 molar fluoride ions. So those are going to be our initial concentrations of barium and fluoride. However, as the barium fluoride starts dissolving, you're going to have a change where barium is going to gain X amount of concentration, and fluoride is going to gain 2X amount, because for every barium that forms, 2 fluorides are going to form. And then at equilibrium, you will have X molar barium and you will have 2X molar fluoride. So at this point, we are going to use our Ksp equation to solve for the concentration of barium in the solution. So the Ksp of this solution is 1.84 times 10 to the negative 7. That equals the concentration of barium, which is X, times the concentration of fluoride, which is 2X, and fluoride is raised to the second power, so we put the second power there. And so now we're just going to figure out what is the value of X, which is the concentration of barium at equilibrium. So doing some algebra, we get 1.84 times 10 to the negative 7 equals 2X squared is 4X squared times X gives us 4X cubed. And now if you do the algebra, you get X equals 0.00358 molar barium. Because remember, X is equal to the concentration of the barium ions. So this is the molar solubility of barium fluoride. This many moles of barium fluoride will dissolve per liter, maximum. We could always dissolve less than that per liter, but this is the maximum amount, that number of moles that will dissolve per liter of barium fluoride. Now, just a quick question. What if I already had some fluoride ions in the solution? What would that do to the molar solubility? Well, if I already had some fluoride ions in the solution, this wouldn't be 0. And that means less barium fluoride would be able to dissolve. This is called the Comet Ion Effect. And anytime that you have ions of the salt already present in the solution, that's going to decrease the molar solubility of the solution. So just keep that in mind as you go through this. So that's where we're going to stop. If you have any questions, of course, talk to me and I'd be happy to help you out. And good luck.